right, good afternoon, chemists. This is your last good afternoon, chemists. Oh no, from Tuesday, who didn't sign the class block would? Okay, a lot of people in the middle, so just make that way throughout the class. I'll have the block of wood at like my review sessions at the final exam, so if you didn't get a chance to sign it and leave a piece of yourself with me, you'll have a chance eventually, all right? Okay, so some announcements before we finish up our last class. All right, so all those final exam resources are posted. I just need to write one more key, but that Carmen exam is in fact posted already for your studying. Remember, our final exam is cumulative. I hope after we finish chapter 13 material today that I'll be able to review some of the new material from chapters 12 and 13 because they are rather long chapters. Yeah, okay. And so looking ahead kind of sequentially, when are due dates for things? Friday is that lab survey. It's worth actually 40 points now. It was 30, but they changed it to 40. So if you already took it, they adjusted the grade, so you don't have to worry about anything. But now it's even more important that you complete that assignment because it's actually a line item in your lab grade book. So I'll make sure to send out a reminder on Friday. Looking ahead for Monday next week, Monday is the last day of classes, but we don't have any lecture that week. But as normal, Monday, we have the last two homework sets are due. They are rather long, but they kind of have to do with the same equations with each other. Gibbs free energy, we used this Q equation, and then in chapter 13, electrochemistry, we used the Nernst equation, which also utilizes Q. You actually see, if you squint your eyes, they are the same equation. Just talking about Gibbs free energy versus cell potential. So those are the last two homework sets. And then at midnight on Monday, that last make your own group project is due. It is a Dropbox. Do not email me your make your own group project. This is to expedite the grading. Since everything is individual, it's a Dropbox because I want to be able to grade them real fast. The purpose of the email so I can give out feedback to the whole group, but this is just a Dropbox. I put it in big bold letters on the assignment itself, so please do not email me your last group project via email. Especially like right before the due date, that would be really bad. And I also just posted grades for group project 4. They were really good. I was really impressed, and kind of looking back to how far you've come in showing your work and showing your units. You've come a really long way, and I'm happy with what skills the majority of you have learned along the way here. And so, all right, that's Monday. Then on Tuesday, that is reading day. It is the last day to submit homework for partial credit at all. Remember, any online homework, whole homework set can be submitted late for half credit. So that means if you complete an assignment, you can get 50% for it. Because if not, that's going to be a big fat 0 in the grade book come the end of the term. So some points are better than nothing. You can even submit partially complete ones for some points, at least, though it will have a penalty. And then finally, Tuesday at 2 p.m., I'll have my review session in here on Zoom, all of that stuff. I just haven't posted the information about it yet. All right, so those are the announcements. All right, and so you may be wondering why I asked for, that the first survey results so quickly, but this is why. One of the questions in the survey that the majority of you completed for me is when I say the word chemistry, what do we think of? And so this is a tradition of mine. Much like the block of wood is a tradition of mine, I like for students to leave a piece of themselves with me before they move on to the next step of their academic career. I want to leave you a gift as well, and that is our class word cloud. So this is what we collectively think of when we think of the word chemistry. And so, we all giggle and stuff because obviously it's not all scholarly words, all right? But what I'm trying to say here is that's okay. That there's bad connotation words, that's okay. Being challenged is okay because when we're challenged, that's when we grow the most. When we overcome challenges and we don't fold from any small inconvenience, that's when we grow the most and gain the most skills. So I'm happy to see that, the bad connotation words aren't super big. So I do this for all of my classes, and in 1220, there's actually very little bad connotation words. They finally, I guess, succumbed to Stockholm Syndrome, I guess, and they've just, you know, they're dealing with it. But here, yes, we recognize that, you know, this class is really difficult, but I think you've all taken it in stride, and I really hope that you take more than just the chemistry concepts away from this class, but the skills that we've built along the way. I'm really excited that interesting is a very big word up there. Interesting, all right? And so I was looking at some of the anonymous posts there of what students thought was like really memorable, really useful from this class, and I'm really surprised by the results. A lot of you liked dimensional analysis, I guess, I don't know. Maybe you don't agree with that, but I do find dimensional analysis to be rather fun, and looking at some of the group, your make your own group projects, a lot of you are doing dimensional analysis, I think, because of like the power that just unit canceling can have to solve a lot of the world's problems. It doesn't necessarily have to be chemistry, right? You don't have to be smart at anything. You can just be really good at canceling units, and yeah. Okay, so there's our word cloud. I'll post this on the last, my last recap thing, so you have something to leave with here. All right, so there's that, announcements. Okay, so let's finish off chapter 13, then do some review. I made a review packet. We're not gonna finish it, but the rest of it, I guess I'll finish at my review session. So if you want, we're not gonna do it quite yet. But this is the link. It's go.osu.edu/1250rev, as in review. And you can download the packet that I prepared for you. But I wanted to show some demos. Oh, wait, they didn't bring me my batteries. Oh, and then we'll blow up some stuff. Yeah. You'll blow up some stuff. Okay, so the demo I was going to show is the last equation that we went over on Tuesday, and that is the concentration cell. Can you bring me the sawed in half battery?
Yes.
Okay, yes. Okay. Yes, okay. So I wanted to show the demo for this concentration cell. The idea is that we have an anode and a cathode, and they're identical. They're both copper. All right? And so when we calculate the standard cell potential, oh wait, this isn't it. That's not it. It's this one. I'm sorry. This is the concentration cell, I'm sorry. So we see that the anode is copper, the cathode is copper. The only difference is that the concentrations are different. So when we use the Nernst equation, we incorporate concentration into the Q component. All right, when we use the Nernst equation, it's E cell standard conditions minus some junk log Q. Q is where we put concentration. So what we can see is the anode and cathode are identical. They're both copper. So regardless of what the reduction potential is, we know that the standard reduction potential is 0, meaning at standard conditions, this cell will produce no voltage because it's the exact same. We have copper and copper. But the thing is actually how the cell is set up are not completely identical. The concentrations are different. And that is what produces a small amount of voltage. And so here we see, because Q is not 1, we actually do produce a little bit of a voltage here because of that concentration difference. So this is called a concentration cell, where we produce a small voltage just from the presence of a tiny bit of concentration difference. So I have that demo right here where the prep lab or the demo team made me a concentration cell. So I can't touch this because how this is set up is that we have really concentrated copper nitrate on the bottom of the speaker and then more dilute copper nitrate at the top of the speaker. It's kind of hard to see, but you can kind of see the gradient there. And so the anode and the cathode are both copper. So it's like a copper strip on the top and then a copper strip on the bottom. So what I'm going to show you here is the voltage of it. So right now I don't have it set up. All right, it's not connected. So you can think of this like the 0, all right, because it's not connected. So oh, you can't see that. So I'm going to connect it now, and we'll see it just via concentration does a voltage, a concentration gradient, a concentration difference, does it produce a voltage. So right now it's 0, and so when I plug this in, We see, yes, in fact, that when just with a concentration difference, we do in fact produce a small voltage just with the same anode and cathode, just the concentrations are different, right? And so it's that concentration difference Q, like a non-1 Q, is what's producing that voltage. I tried this in the previous class, but it didn't work that well. So what's producing the voltage is the concentration difference. What will happen if I mix this up? What happens to the concentration if I just mix all of this up? Concentration becomes uniform, yeah? So will I have a concentration difference if I mix it all up? Nope, so Q will be what if I mix it up? 1, so what do you think the cell potential will be? 0, yeah, so let's see if that happens. It didn't, it kind of happened last time. Yeah, there we go. Yeah, so I mixed it up, made the concentration the exact same, and we see it definitely went down, right? That once I mixed it up, got rid of that concentration gradient, the voltage definitely went down closer to 0. Okay, there's the demo, perfect. Okay, turn you off. Okay, so let's move on with the rest of the chapter, and this is where we're going to talk about batteries. All right, so this is application of electrochemistry. All right, and I think this is rather important because Honda is building a new EV, electric vehicle battery plant in Grove City. They're investing billions of dollars into the community, into the Columbus community. Does anyone else want it? Anyone else want it? You want it? Okay. And I think there's definitely a non-zero number of you who will probably work in this Honda facility sometime in the future. So hopefully these slides will be interesting to you. All right, so we're going to talk about batteries and fuel cells. So when I had that copper and zinc electrochemical cell and the little flag spinning, technically that was a battery. It's a spontaneous cell. It holds voltage that we can use to harness and do work. That is a battery. That's essentially what a battery is a self-contained galvanic cell that's a spontaneous cell that we can harness at any time. We can take those electrons to do work for us to power our devices. So batteries or fuel cells, we'll talk about in a minute, are essentially just spontaneous reactions. All of these have positive cell potentials, all of them. Right? The big difference between batteries is whether they're rechargeable or not. The idea is, okay, there's like cheap Duracell. Actually, Duracell's not that cheap. It's rather expensive. But Duracell batteries is a type of technology in chemistry that is non-rechargeable. Once you spend the reaction once you spend all of that voltage, you can't get it back. That plugging it back into a socket won't get you a recharged battery back. Versus you can go to the store and buy much more expensive rechargeable batteries. Those are what we call secondary batteries that are rechargeable. That's the big difference. Where a rechargeable battery, yes, we plug it into a socket and we can get that energy back and store those electrons. The big difference between a primary cell and secondary cell is when we do electrolysis, essentially give the reaction electrons by plugging it into the wall. A primary battery, we spend the reaction. We go from A to B to get our electrons. But once we try to recharge it, B just becomes something else. So that's why we can't get our energy, our battery juice back. Like, have you ever tried to recharge a non-rechargeable battery? Maybe. It doesn't work because the technology is not there. This reaction is not reversible via electrolysis. Versus secondary batteries are, where you can spend your battery, you go from A to B and get your like electricity, but then once you plug it into the wall, you can go back from B to A just by plugging it into the wall, so like electrolysis, right? So that's the big difference between primary cells and secondary cells, and where we distinguish them is via their technology, the chemistries behind it. So a lot of these slides are kind of review of reactions, but hopefully you can relate it to your everyday life. We'll also talk about the hydrogen fuel cell. We've seen this reaction many, many, many times, and we'll see it today as well. But in a hydrogen-fueled vehicle, this reaction occurs under much milder conditions, and where we get the energy is via redox and not combustion. So let's talk about our types of battery and review a little bit. So the first one is an alkaline battery. So I tell you the anode and the cathode. I tell you the reduction potentials. So what is the total cell potential at standard conditions? Remember, cell potential is always cathode minus anode. So we are going to do cathode 0.15 minus negative 1.28. And that equals something. Can I do that math in my head? No, I can't. I'm not smart enough. So we see, okay, 0.15 plus 1.28. We get that the standard cell potential for an alkaline battery, this is your like cheap Duracell battery, the batteries at the self-checkout lanes at Target, is equal to 1.43 volts. That's at standard conditions. That's from, our table value. But if you go to the Duracell website, look at the packaging, you'll see that the manufacturer only reports a voltage of 1.5. That's different than our table value of 1.43 that we just got. Why do you think it's different? We're not at what? So we're not at standard conditions. Yeah, remember that dot that we calculate from table values means standard conditions, means 1 molarity of everything. Do you think the manufacturers put 1 molarity in those batteries? No, they pack it with higher concentrations to get more juice out of it. So we see we're just not a battery is not at standard conditions. So that's why it differs a little bit, but not a lot. Standard conditions. Right? So that's an alkaline battery. Alkaline means basic. You see the electrolyte is potassium hydroxide. So this reaction, if we went to balance it or whatever, is balanced under basic conditions. And I think this is quite funny because whenever I'm grabbing like an old device and I open it up and I see that it's all crusty in the battery compartment, and sometimes my friends or family will be like, oh, be careful, like that's battery acid, don't touch that, like wash your hands, be careful. But here's the thing, regular alkaline batteries, we just learned, is acid seeping out of those batteries? No, it's actually battery base, yeah, so the stuff in the crusty stuff in the compartments of like old remote controls or old toys, it's actually base, not acid. Where acid comes into play is the next one, a lead acid battery. This is a secondary battery. It is rechargeable. This is the battery that is in your vehicle. Those 12-volt batteries that start your start plug, so it turns over your vehicle and it gets recharged by your alternator as you're running your vehicle. These have to be rechargeable because we don't want to have to recharge and plug in just a regular conventional vehicle. They're supposed to be like self-contained motor vehicles that should, in theory, have minimal maintenance to it. So a lead acid battery is a type of technology and chemistry that is reversible, that once this reaction at the anode and cathode go forward, if you plug it in and supply electrons via electrolysis, you force the reaction in reverse, basically storing energy again. And so our lead acid battery here, if we calculate cathode minus anode, I think we get something like, so cathode is 1.69 minus negative 0.36, and so we get something like 2.05 volts, right, for a lead acid battery. But that's just one lead terminal, because if you know anything about, car batteries, what's the voltage on a car battery? 12 volts. So how do they get the 12? Well, they probably put 6 of them in series next to one another to get that upped voltage. So the big difference here between our cheap and more expensive, or like our cheap alkaline batteries, non-rechargeable, those lead acid batteries are rechargeable, typically aids to being more expensive. All right, let's talk about some other technology here. Nickel cadmium batteries, these are another type of rechargeable secondary battery. In this day and age, we want things to be rechargeable. We're in the day and age of convenience, not just technology, but we want our technology to be convenient. And so these nickel cadmium batteries also are rechargeable. An example of where you're going to find them are like solar lights. Okay, so solar lights, like I popped a bunch of mine open to clean them out for the spring, and solar lights, you want those batteries to be rechargeable because they have to charge during the day and discharge during the night, and you want them to just kind of be a forget it, like set it and forget it type of thing. So nickel cadmium batteries, these yellow ones, are what you'll find in like low voltage devices like a solar light. Doesn't require a high amount of voltage. We see nickel cadmium also is in basic conditions, and here is our cathode and our anode. So if we calculate E cell, so that's our cathode, there's our anode. If we do cat minus anode, so 0.49 plus 0.76, we get 1.25. Right, 1.25 volts. So we see again that voltage is a little bit off from our manufacturer. But what we also see here is that these nickel cadmium batteries have an overall lower voltage than our standard alkaline batteries, 1.5. So if you try to replace all of your batteries with nickel cadmium, because of the lower voltage, you might get poorer performance in some of your devices. That an alkaline battery has rather a higher amount of voltage, 1.5, that allows us to run our devices. I think an example is like I have a lot of like headlamps for things, and I thought I'd be clever and like replace all of those batteries with rechargeable ones. But what I found out is that that lower voltage with rechargeable batteries deteriorated the how long the headlamps worked. And so basically I could not one for one just replace all of my batteries in those headlamps with rechargeable batteries, unfortunately. I tried to be clever and cheap about it, but guess not. All right, so here we see nickel cadmium, 1.2 volts. Here's an example of a battery pack that's like in the back of a like a rechargeable phone, like one like a home phone, one with like a rechargeable base. And so if you look here, it says that it's nickel cadmium, but it's 12 volts. It's a 12-volt battery. So if this is nickel cadmium technology, if you look closely, how we're getting those 12 volts is if you look closely, look, there are 10 batteries in there. So those 10 batteries are all wired in series to one another to up that voltage. So here's another example. Do I have this? No. Okay, here's another example, all right? So yes, the regular Duracell batteries you buy at Target or whatever are 1.5 volts. What about the batteries that are in a smoke detector? What do we call those batteries? The ones that look like little cube things? The ones that if you lick the side of it, then you get a nice little shock? Do we know what voltage that is? That's a 9-volt battery. That's a 9-volt battery. So like you've never thought about doing that? So one of these batteries? Right, that's in the back of your smoke detector. And so here are the anode and cathode, right there, yeah, or you put them both together and then big sparks fly. Yes, that too. But here, the positive and anode terminals are right together. So I don't know, that the scientist, the curious scientist in me wants to complete the circuit maybe with my tongue or something. But if you do, you get a nice quite shock. It's a 9-volt. 9 volts in our 9-volt battery. So this technology is also just a simple alkaline battery. But where does it get the 9 volts? Well, I cut open one for you, and so you can see it. This is what a 9-volt battery, the inside of so this is my 9-volt. So where's my camera? There it is. See the 9-volt? Okay. So there, don't lick it, but yes, in theory, if you complete the circuit with your tongue, you'll get a nice shock. But here it is, cut open. What is that? Those are 6 just regular alkaline batteries inside of a 9-volt battery. An alkaline battery has a voltage of what, 1.5? 1.5 times 6 is 9. This isn't a so one of these batteries, it's not a triple A, it's actually a quadruple A. It's basically a little bit smaller than a triple A battery. But yeah, there's 6 of them in there, just all wired in series. Yes. And so I know there's a lot of ECE people out there, and so hopefully this chapter gives you some love. So connecting batteries in series will up your voltage, but connecting them in parallel increases your capacity, right? Capacity, something like that. So for example, me and my husband, we have an RV that we fix up. It's like half broken all the time, and so we have to fix it. So we just purchased more batteries for it because we are millennials and we like to have power when we are not, when we're kind of off on our own camping. And so we bought, instead of buying like one really big deep cycle battery, because those are expensive, we bought 2 smaller ones and connected them in parallel. So we would have a larger capacity. We didn't want higher voltage. We wanted like a bigger battery, but we didn't want to pay that much for one. So we just bought 2 smaller ones. There's 3 things I kind of hate in life. One of them, and if you've already heard this story, one of them is people with chemophobia. The second is electricity. Electricity scares me because I can't see them. I can't see the electrons. I like electrons when they're like discrete and there's only one of them, but electricity scares me. There's so many times I've been shocked or completely, like literally shocked by something because I don't understand the electrical diagram, the wiring diagram. And then the third thing I hate is Honda ridge lines. It's the third thing. So if you are wondering about that, you can ask me after class. But usually I get a laugh, no? Like, why Honda ridge lines? Like the vehicle? Okay, anyway, okay, so let's talk about, on the case of vehicles, lithium-ion technology. So in every rechargeable device, most of our things are rechargeable nowadays. I told you we're in the business of convenience now. Lithium-ion batteries, that's the technology in our phones, in Teslas, in our iPads or laptops. Here, these lithium-ion batteries are utilizing a really easily oxidizable substance, lithium. Lithium is really easily oxidized. We have a really negative reduction potential. Lithium is very reactive. That's why there's so much concern with, lithium batteries exploding. It's because lithium is exploding, that's why. So, but the good thing about lithium-ion batteries is look at this voltage. It's a crazy high voltage, 3.7, all right? And so we're able to get a lot higher voltages with lithium technology because lithium is so reactive. But there's that trade-off, right? Reactivity, yes, we get higher voltage, but it seems unsafe, less safe. Like I was just looking at this TikTok video of a guy, he like dropped his, like a dumbbell on his phone, and then like 3 seconds later it exploded. Did you see that? Yeah, I know, it's crazy. It's because, yeah, we are carrying around little lithium bombs, okay? Lithium bombs, and just like some type of tap, we see that these batteries, they get all swelled because of the lithium that's in it. If you ever purchase something from Amazon and you see like big red tags that say, do not like take on an airplane, only ground travel only. It's because of the lithium. Lithium is not allowed in the underbelly of a plane because if it explodes, no one's there in an underbelly of a plane to like fix it. But lithium batteries are allowed in like the overhead, like your carry-on, because if it were to explode, at least there's people there to like extinguish it. All right, so basically there's a lot of regulation about lithium battery travel. It's so well used, but it's understood that it's very reactive. So if you calculate the overall cell potential, we see, cathode minus anode, 1 minus -3, we get a standard reduction potential of 4 volts, but what manufacturers report is 3.7. Right? So Tesla vehicles are made with lithium-ion batteries, but a bunch of them wired in series in order to up the voltage in order to get enough power to go from 1 to 60 in like whatever seconds? I don't know. Okay, so that's lithium-ion technology. Here's the thing. As scientists, we're always innovating. There's always issues and things that we can improve. All right? So lithium. You know, there's a lot of ethical concerns about mining lithium. If we look at the cathode, cobalt, also ethical implications. It's, a scarce material for cobalt. So, scientists, researchers are constantly trying to replace materials with cheaper things, with more economical things, with more ethical things, but we still want our devices to have the high voltage that we see. Like, we don't want to replace the anode with something and then completely trash our voltage. Then that's not a good replacement. So here's an example of kind of a story of lithium-ion technology that's really happening in real time. So whenever I watch YouTube videos of like some of my outdoorsy people, they always are like sponsored or whatever. I hate sponsoring things. They always have those stupid plugs, and then I like shut my ears. But anyway, one of the people I watch, they are sponsored by Blue Yeti. Do you know Blue Yeti? Yeah, it's like those portable battery packs. So Blue Yeti is a brand of battery packs. So like you can literally take this big heavy battery pack and plug in like outlets and stuff like electronic devices into it. It's a big beefy one, but this brand is known for being more rugged than other ones. And I was wondering why. Why is Blue Yeti more rugged than, let's say, Jackery or whatever? So another kind of concern with lithium ion technology. What happened to all the Teslas this winter when it got real cold? They what? They ran out of battery, or their batteries didn't work. They were stranded. There was a bunch of Teslas on the side of the road just because it got real cold. So why? And why is Blue Yeti and this lithium technology different? So Blue Yeti uses the technology lithium iron phosphate. So this is still a lithium battery, but what's different is that they changed the cathode from cobalt to iron. Iron, super plentiful. Rust, that's everywhere, all right? So here we were able to change that cathode to make it more, maybe more sustainable, more achievable, maybe even cheaper. Also what happened here is look at the electrolyte, lithium aqueous in a lithium ion battery. What does aqueous mean? Dissolved in water versus in lithium iron phosphate. This is basically the new family of lithium battery technology. It's like the next generation is lithium iron phosphate. Its electrolyte is an organic solvent. So when we think about the freezing point temperature of water versus an organic solvent, water has a much higher freezing point temperature. It will freeze first. It freezes at 0 degrees Celsius versus organic solvents typically have a much lower freezing point. So with that in mind, does it make sense why all those Tesla vehicles basically were disabled in really cold weather? It's not because their batteries ran out of juice. It's actually because their electrolyte froze. And if their electrolyte froze, then is your salt bridge complete? Can those ions move and complete the circuit? No. So once your electrolyte is frozen, then you don't complete your circuit and you don't have a functional battery. All right, and so that kind of, looking at the technology between, Blue Yeti, looking at lithium iron phosphate and some of the pros there, the solvent is one of them. That Blue Yeti being the rugged battery type, I could see why that these batteries are much better performing under harsh, really cold conditions just because of the solvent type, that your electrolyte won't freeze as easily if it's organic versus if it was water. But what one of the trade-offs is look at the voltage. It's a little bit lower. It's still rather high, in the 3, but not as high as a lithium ion battery. Right? So yeah, you might face some troubles with lithium ion batteries if it gets really, really cold, all right? Much lower than 0 degrees Celsius. Once your electrolyte freezes, then you've essentially, you've gotten rid of your salt bridge, that your ions can't complete the circuit. Yes. How might this affect battery operation in cold weather? Okay, water freezes in your lithium ion. Okay, so you see between lithium ion and lithium iron phosphate, we changed the cathode to kind of be a little bit more environmentally friendly. So kind of what do you think like the next step is? Let's replace the anode, all right? So maybe instead of lithium, we look into a different type of technology, maybe potassium or sodium. That's actually done at this very university. There's some chemistry research groups that are looking into making batteries in air. It's called potassium air batteries. So potassium is the anode instead of lithium. We can see why would they choose potassium. It's in the same group, has the similar reactivities as lithium. But their whole spiel is that it happens in air. Okay, all right, batteries, good. All right, so what else about batteries? So, we look at voltages, like freezing points and electrolyte types, but really it comes down to cost and convenience. Okay, so you might be wondering, well, why don't we just line our electric vehicles with a bunch of lead acid batteries? Lead acid batteries are secondary rechargeable batteries. Why do we have to use lithium ion? It's because the energy density there. All right, that lead acid batteries have a very low energy density that you basically, for the same weight of a lead acid battery, you get much less energy storage than a lithium-ion battery. So that's what we mean by energy density, that you can have a really lightweight, that's why our phones are so lightweight, yet they last for so long. Lithium-ion has a very high energy density. You can hold a lot of energy storage in a small space. But with energy density comes price. So here are the different prices per kilowatt hour for these different batteries. Though I will point out this slide is probably 2 years old, so I would say just double all of these costs. An alkaline battery, let's say about 50 to 100 kilowatt hours or dollars per kilowatt hour, so it's the one of the lowest here. Lead acid is very similar. It's so heavy that it's just really inconvenient to use rather than an alkaline battery. But once we go into other rechargeable batteries like nickel cadmium or nickel metal hydride and lithium ion, it gets much more expensive to deliver the same amount of energy just because the materials are expensive. Compare this to just plugging straight into the wall, all right, where there is no battery storage. We are limited by where are there outlets for us. We are paying maybe double this value, cents, pennies per kilowatt hour if we're just plugging into a wall. We're really paying for that convenience of having portable energy storage. So like I said, when we did these demos up here, these cute little galvanic cells, they are technically batteries, but these beakers are not very portable, but batteries are. But that's what they are. Batteries are galvanic cells. So energy density, battery cost, and thinking about replacing anode and cathode material, we also look into how scarce, what's our supply of different materials. We don't want to be using materials that are in this critical zone, hard to find or maybe not ethically sourced. Finding elements down here, nickel, are good alternatives. So going from cobalt to iron for lithium iron phosphate batteries is definitely an attractive thing since iron is so much more plentiful. Now we just got to wait for the price to come down because I'm pretty sure that lithium iron phosphate is a little bit more expensive than lithium ion just because of how new it is. All right, so talk about the last type of, it's not a battery, it's a hydrogen fuel cell. Really, it's a redox reaction that produces a voltage. And we've seen this reaction a lot before. So this is a little bit different. There is hydrogen technology out there. I believe there is one hydrogen vehicle, some bus that OSU has that picks up students and stuff to give a zero emissions type of vehicle. So let's look at those hydrogen vehicles. So these vehicles don't work off of battery power like a Tesla does. It works off of a redox reaction between hydrogen and oxygen instead. So you still have to gas up this vehicle with hydrogen. But a redox reaction is still happening. So you still have to gas up with hydrogen, but let's look and balance this overall reaction. All right, hydrogen gas gives off 2 electrons, but then those oxygen molecules take those 2 electrons. So if we cancel stuff out, we see that in a hydrogen fuel cell, the reaction that happens is 2 hydrogens plus an oxygen gives us 2 waters. So if we calculate the cell potential, we get, so this is your cathode, this is your anode. So the anode is 0, so our standard cell potential is 1.23 volts. So a hydrogen fuel cell produces about 1.2 volts of energy just by taking hydrogen and oxygen, reacting them in a redox reaction under mild conditions. Where their electrons are just being transferred at a slow pace to produce this voltage. Because we've done this exact same reaction right here, right? I have this balloon, it's filled up with hydrogen and oxygen, but when I ignite the reaction, it happens almost immediately. All those electrons are transferred immediately and not under mild conditions. But technically, it's the same chemical reaction, but in a hydrogen fuel cell, we're utilizing the voltage that's there. And so I'll just clarify here that when it comes to hydrogen technology, we can either utilize the combustion reaction, right? And that's just like a regular combustion reaction, or we can utilize the redox reaction. So there are two types of vehicles out there. One of them is a hydrogen internal combustion engine. This is no different than just like a regular gasoline engine, but we use hydrogen, usually it's dirty hydrogen, to run the pistons in your engine. It's no different than a regular engine. We are limited by the 40% efficiency for most internal combustion engine vehicles. That's still hydrogen technology, but it's not a mild redox reaction. When we talk about hydrogen vehicles, usually people are talking about redox reactions. Usually they're talking about fuel cells. They're not talking about combustion reactions that we've known and loved. When talking about hydrogen fuel cells or hydrogen vehicles, we're talking about redox reactions. And so again, in a hydrogen fuel cell, you still need to supply hydrogen and oxygen, but it's a redox reaction. There's no internal combustion. All energy comes from that electron transfer. And in order to produce a high enough voltage to like run your vehicle, we put a bunch of them in series to get a high enough potential there. But what's nice about hydrogen fuel cells is it's 2 times more efficient than internal combustion engines. But really the drawbacks of hydrogen vehicles is look at how you're gassing up your car. You're gassing it up with a gas. It's hard to store gases. So when I was reading all of your reasonings of choosing the best gas fuel source for that last group project, many people put methane because it was the least carbon footprint, the highest energy density or one of the highest. But here's the thing, it sucks working with gases. And they're dangerous. I don't want to have to it's easy to carry around a 5-gallon thing of gasoline because it's a liquid, but working with gases, that's much harder to contain. So you will also want to think about, it doesn't mean that your answer was wrong. It's just you want to think about convenience as well. We don't want to be working with, going to the gas station to actually get a gas, much more difficult than when it's a liquid. So just keep that in mind. It's not like I docked you or anything. I just want you to kind of think about it holistically there. All right. Oh, okay. Ooh, oh my gosh, last slide. Last slide of this chapter, because we already went over electrolysis, and then I'll blow up some stuff. And that is, I want to finally complete the circle on catalytic converters in cars, because the catalysis in a catalytic converter is actually catalyzing a redox reaction, actually multiple redox reactions in your vehicle. So a catalytic converter in a regular internal combustion engine car, when it's working properly, is actually catalyzing 3 different redox reactions. These are called 3-way catalytic converters. The 3 reactions that a catalyst in your vehicle catalyzes, one is the oxidation of carbon monoxide. Carbon monoxide is no good. So it's a good thing when CO goes over your cat in your car and gets converted to CO2. I mean, CO2 isn't good either, but CO, carbon monoxide, is deadly. CO2 is less deadly. It's just a pollutant. So here, converting CO to CO2 is a good thing for your catalytic converter. The second reaction it catalyzes is it oxidizes uncombusted hydrocarbons, so like methanes or ethanes or something. Gasoline is long hydrocarbons, so any short pieces that are uncombusted also get converted into CO2 as well. These uncombusted hydrocarbons can contribute to birth defects, other types of pollution, so converting it to CO2, again, is a good thing. And then the last thing it catalyzes is the reduction of NOx, so NOx gases. That's a bad thing. When NOx gas gets into the air, it reacts with water and becomes nitric acid. And that's a bad thing. So if you breathe in NOx air, NOx, and it comes in contact with the water in your lungs, it becomes nitric acid in your lungs, and that's bad. So what a catalyst converter does is take those NOx gas, catalyzes, reduces that NOx to just nitrogen and oxygen, and that's a much better thing to be putting off of your tailpipe. And so here's the thing, we have 2 oxidation reactions and 1 reduction reaction. In a properly working catalyst in your car, all 3 will be running simultaneously at the same time. That electrons from your oxidation reactions funnel into the reduction reaction of reduction of NO2. So the idea of, running a properly tuned, engine where you're consuming fuel and oxygen is efficient is really important, because when your vehicle has like that perfect fuel to air ratio, or air to fuel ratio, I think it's like something like 14.7 or something, is the perfect air to fuel ratio for a properly working engine, where you're not running rich, you're not running lean, you're right there in the middle. Because when you're right there in the middle, you favor all three of those reactions. Because when you run lean, you have too much oxygen, you have complete combustion, you're not, you're favoring reduction of NO2 and not the oxidation reactions. Versus if you're running rich, you have not enough oxygen, way too much fuel, you'll actually emphasize the oxidation reaction of uncombusted hydrocarbons in your catalyst, and you'll run out of electrons within all of those processes. We need all three to be running at the same time for your catalyst to run properly. And so again, your catalyst is good. Please do not take out the catalyst in your vehicle. I know it makes your car sound louder, but it's there for good reason, to prevent, things like air quality, acid rain, water quality, and birth defects of pollutants that are out there. All right? So do keep your catalyst on your car. I only say that because every year a lot of engineers, they tell me with pride that they take out their cat, but that's not a good thing. Yes, you can make your vehicle sound louder, but that catalyst is in there for good reason, to protect our breathing air. That's there. Okay. So that's it. Those are all of our slides for Chem 1250. Yeah. Yeah. No, don't clap. Not yet. We still have some stuff to do. So I just wanted to end the class and our material with some inspirational stuff. I'm not going to do the thermite reaction, so I brought the thermite reaction back from popular demand, but we'll end this class with some boom boom. But I wanted to also talk about some inspirational stuff that you can take with you, right? I hope that you take not only just chemistry content from this class, but more skills. I hope that I've bashed those misconceptions you have about chemists or scientists. I hope only 2/3 of you said you felt like a scientist, right? And I'm disappointed. Maybe it'll change right now. I hope that me yelling at you twice a week has convinced you what a scientist, what a chemist looks like is not what we've always thought. It's not that like nerdy guy in a lab coat. It can be whoever you want it to be. It can be you. Right? Because a chemist, a scientist, all you need is to be curious and to have scientific inquiry and constantly question the world around you. That's what you need. So I have these pictures up here because I think media does us dirty, us chemists. They always portray us as evil people, and that's what all these pictures have in common. Snape, he's the alchemist guy, right? All right? But he had the hero arc at the end, but let's all agree, he was a bad guy for like most of the movie, all right? Plankton, he was like, the smart scientist, evil genius or whatever, but was also SpongeBob's like arch nemesis for being so smart, Walter White, he was a chemist, a chemistry teacher turned drug lord. I actually never watched the series. And what's funny is isn't he, I've never watched it, but don't sometimes you think, oh, maybe he's a good guy, maybe he's a bad guy, you kind of flip back and forth? Kind of like a what? An electron. Because what was his nickname? Heisenberg. And what did we learn about this year? The Heisenberg uncertainty principle, where you can't know the location of electrons. Yeah, boom, right? Okay. And I've never even watched the movie. I just knew when they're like, oh, his nickname's Heisenberg. And I'm like, oh, like the electron. Okay. And then this more latest one, not even, the first Wonder Woman. All right, where like the one nemesis person, they invent like an asphyxiating gas that goes through gas masks, right? She was like the evil scientist. But here's the thing, she was the evil chemist, but they're not even creative about her name. Her name is Dr. Poison, like that's not even creative. So yeah, I'm just saying society does us dirty what chemists, but I hope what you take from this class is what a chemist looks like is different. It looks like you. It looks like whatever you want it to be. A chemist can, wear heels as high as they want, or their body can physically take. And that's what a chemist looks like, and it can be you. So that's kind of why I walk into every class and say, good afternoon, chemists, regardless if you feel like a chemist or not. I think that everyone is a chemist in this classroom. But I will point out, I know that media does us bad, but there is one example I can think of where the chemist is a good person. This movie? Yeah, yes. Yeah, Big Hero 6. I love this movie. And so Honey Lemon, she's a chemist, right? She's a chemist. She's the good person. She's awesome. She's overpowered. She can do her little thing on her purse and make like bombs during battle, dependent on what kind of property she wants, right? She's the good guy. So there's an example. There are other examples too. I just like Honey Lemon because me and her have the same energy, I guess. But I'll point this out. One last slide here. Here's a meme I found, or like a thing from Tumblr, but I don't agree with this. So here's Honey Lemon in battle with her little periodic table purse. But here's the thing, that periodic table only tells the composition of the substance. What did we learn about chemical properties this year? Is it just composition that tells us chemical properties? No, it's composition and structure. So when she's there with her purse, she's only saying the composition, not the structure. So technically, is this movie believable? Could she solely just use the periodic table to make the bombs that she wanted with certain properties? No, she couldn't. She would have to be able to communicate structure as well. So that movie's not super believable. Okay, sorry about that. All right, so that's basically my end of spiel to convince you that chemistry is cool. So I hope that your understanding and appreciation of chemistry has changed this year. It's been a really fun ride. I love teaching engineers every year. One, because I get all of you to myself and I can do whatever the hell I want. And so if I want to yeet out concepts, I can. If I want to blow up stuff all day, I can. And that's what we're going to do right here. And so let's review a little bit of these reactions that we're going to do. All right, so we've done the hydrogen balloon experiment many, many, many times. But look and see and relate it to electrochemistry instead. Is Brandon here? He wants to do the demo. Brandon? You don't want to do the demo? Okay. So our hydrogen-oxygen balloon, I'll do this one if he comes out. The hydrogen-oxygen balloon, hopefully we can look at this from an appreciation of electrochemistry. Yeah, I'm going to do the hydrogen one first and you do the other one. Okay, so hydrogen in our hydrogen balloon, is it being oxidized or reduced in this reaction? So hydrogen H2 is starting off as 0. And then in water, hydrogen has what oxidation number? +1. So it is being oxidized. Great. Oxygen, on the other hand, in the first reaction, in the hydrogen balloon reaction, oxygen starts off as what oxidation number? 0. And then in water, its oxygen is what? -2. So oxygen's being reduced. Therefore, oxygen is what kind of agent in this reaction? An oxidizing agent. Oxygen gas being an oxidizing agent? Yeah. Because it's reduced in the reaction, so that makes sense. So let's do this hydrogen balloon reaction first. Remember, this is amongst gases, so if you blink, you will miss it. You will miss it. So let's turn off everything so it can be more ambiance or whatever. And then, so let's do the ears. Remember, this is very, very loud. Very loud. Yes. Okay, all right. Hydrogen balloon. We started with the bang, now we're going to end with the bang. Jeez. Yay! Okay. So now we'll do the thermite reaction, which is amongst gases. So in this reaction, can you blink? Is that okay? If you blink, will the reaction just go by? Everything's amongst solids, so the reaction's going to be a lot slower. It's still going to, finish eventually, but it's going to be slower. So you want to do it? Yes. Okay. So this is one of our demo people, Brendan. He's been helping me all year. He's always made sure that the demos have been extra good for you all. And he's a graduating senior, so he just wanted to be able to do the thermite reaction. So let's enjoy it.
All right, well, you guys have probably seen me a lot in my code, so this is the last time, so send it off, and go off and bang.
There is no bang. It's just real bright. Oh, so remember, this light is just the fuse, the magnesium, to start the reaction. Come on, dude. I believe in you. But here's it's just going to go. Oh no, is it going out? Careful with your face. No, it's probably going to go out. Oh no! Can you make another one? We still have, how much time is left in class? 3:15. We still have, oh geez, okay. We still have like 25 minutes in class. No? Okay. We'll make a new one. We still have 25 minutes. Okay, all right. Okay, we'll come back, reconvene. Brandon needs to. Oh man. Okay, I just guess Gibbs free energy, we're just not spontaneous, that delta S of the universe was negative for a moment. All right, so when he comes back, so we still have like 25 minutes left of class. Let's do some review. So if you haven't grabbed the slides here, please do that. Just it'll make things easier for us. So this packet just has a cumulative array of questions. So my question for you is, what chapter do we want to start with? 1. Do you want to go over 12 and 13 at all? Or do you want to just start back at 1? What do you want? Who wants to go back to the beginning? Who wants to start at 12? Okay. We're going to start at 12. That's what I was prepared for. So let's just start at 12. I'm sorry. So we're going to start at chapter 12 because this is all new material. Don't worry. We will do the rest of this packet at the review session next week. All right, so I'll finish the packet then for whatever we don't finish. So if we're reviewing, then I'm sitting. So chapter 12 is about chemical equilibrium, where we have these elementary reactions. We simply can just take the products, divide by the reactants, and ensure that stoichiometry becomes coefficients. But these Kc expressions usually convey concentration. So we only want to include things that either have concentrations, or if we're talking about Kp, pressures for gases. So our Kc expression for this reaction is the concentration of C to the 1, because there's 1, the stoichiometry is 1, D concentration, so the two products, over the concentration of A, but do I include the concentration of B? No, because it is a solid. We also do not include liquids. Those don't have concentrations. All right, so there is our Kc expression. If there was like a 2 in front of D, then I would put a 2 coefficient there. All right, so stoichiometry becomes exponents. Okay, so what does the value of K tell us? K is always a positive number, but it's always either big or small. Because if you look at K, it's just the ratio of products to reactants. Having a negative K does not make sense because you can't have a negative concentration. You either have big numbers up top or big numbers on the bottom. So the magnitude of K tells us something. If Kc is small, that means what dominates, products or reactants? Reactants, yeah. So the reactants is much bigger because K is simply products over reactants. Honestly, if you just memorize that and understand magnitudes, then you're good. That's like 50% of chapter 12. So if reactants are more dominant, that means we don't make a lot of products. So what rate constant is larger? Is the forward rate constant big? No, it's not, because if we don't make a lot of products, that means the forward rate constant is really small. So the reverse rate constant is really big, right? And that's because K equals products or reactants, but it's also equal to the forward rate constant over the reverse rate constant. So the value, magnitude of K, Kc equilibrium constant, not only tells us the relative amounts, concentrations of products and reactants, but also rate constants. Okay, so what if Kc is large? What dominates? Products. So then which rate constant's larger? Forward. Yeah, in order to make a lot of products, your forward rate constant has to be big. So that is just typical, interpreting those values. Okay. All right, so let's use the same chemical equilibrium. This is 19. And now let's say we're initially at equilibrium, but now let's disrupt this equilibrium and ask ourselves, how does this reaction need to shift to go back to equilibrium? So for this question, you can simply just use the quick and dirty way for Le Chatelier's. If you add A, you're adding a reactant. So that means your reaction goes which way, forward or reverse? So we're adding a reactant. So the reaction moves forward. Whatever you do to the reaction does the opposite to undo it. So if I add A, the reaction's going to move in a direction to remove A. And so that's moving it forward. What if I add B? What happens to the reaction? Nothing. Yeah, why is that a trick question? It's a solid, yeah, so solids are not in the K expression. The reason adding A shifts the equilibrium is because the moment we add A, we change Q, and then the reaction has to get back to K. But by adding B, we're not actually changing the value of Q. What if we add D? Backwards, because it is a product. What if we remove C? Forward. What if we increase the temp? So this one's tricky because you have to look at other outside information, and here it's that this reaction is exothermic. So we have to put a triangle in the correct space. Exothermic reactions release heat, so it's a product. So you can just think, oh, triangle's a product, so you add triangle, the reaction moves backwards, goes backwards. Good? All right. All right, so the rest of chapter 12 had to do with pHs, acid bases, and free energy. So let's go over pH calculations. So pH, or whatever, is just a function. pH is negative log of the H plus concentration, where POH is the same, but it's OH minus concentration. Right? And what's special about these numbers is at 25 degrees Celsius, pH plus POH equals 14, and it's because of Kw. Kw is 1 times 10 to the negative 14 at this temperature. That's where the number 14 comes from. So if we want to calculate the pH of these solutions, we just need to be clever and recognize, okay, am I working with an acid, a base? And then finally, is it a strong acid or strong base? Those are our 4 different options. So this first one, HCl, is a strong acid. Is it good?
We're going to see. I made this one personally. So.
Who made that one?
I'm not going to throw.
Okay, we're not going to throw anyone under the bus. Okay, we'll think about, right now? We're going to do it right now?
Do you want me to wait?
No, we can just do it right now. Yeah? Yeah. Lights, cameras. Okay, it's not loud, so I can just.
Yes. Stand right there.
Yeah.
Move a little stuff away.
Okay, let's just, we're doing the second reaction, rust, aluminum. This is also a redox reaction. Sorry, I have to make it like.
Don't look right at it, remember.
Oh, yeah.
Because it's, again, very bright.
Yeah. This is the magnesium fuse. It's like the eclipse. Did anyone else's eyes hurt after the eclipse? Oh, jeez. Yay! Yay! All right, so I'll point out, see this eerie glowing? That eerie glowing? That is the molten iron that's coming out. Look at the product. It's iron. 2 irons are produced. It's in the liquid phase because it's so dang hot. But it's glowing also just because of how hot it is. It's actually black body radiation. It's the same type of phenomena when we turn on our stove, like our electric stove, and the rings get really red hot. So what you're seeing, that eerie glow, is that red hot from that iron, just like red coals that you see, or if your engine is running really lean and it gets really hot, then it turns cherry red. Your exhaust pipes, you ever see that? Maybe? Yes. Yeah, because it gets real hot. That is black body radiation that you're seeing when it gets real hot like that. All right, so yeah, that was Brandon's last thing. So I'm glad that he was able to get it done. So sad that he's gone, and I'm glad that you all got to see that he prepped all of our labs, because they were always, or demos, they were always very good. Okay, so let's just continue. How much time do we have? 15 minutes. Okay, cool. Okay. Do you know where I went to see the eclipse? Oh, did I tell you all? Oh, you heard me? Yeah, it was a Costco parking lot. So there are 3 Costcos in Columbus. My typical Costco is the Easton Costco, but only 2 of the Costcos were in the path of the eclipse. So I just went to the closest one, the one in Polaris, and I got to see it for a couple minutes, and there was no traffic at all because I was right on the edge, and I got to eat a whole pizza and an ice cream in the parking lot and watch it. It was great. What? I like to get the vanilla with the strawberry on it, but I go light on the strawberry. I'm a real fan of just like plain vanilla ice cream because I'm like really boring. I save all my energy for class, but as soon as I leave the room, I turn it off. Yeah. Yeah, okay, all right, so what are we doing? Reviewing, okay. All right, pHs. So the strategy here, recognize HCl is an acid, and it's a strong acid, so we can make an assumption that this concentration is also the concentration of H+. So we can simply just say, oh, the pH is equal to negative log of that that HCl concentration, so 0.012, and then you get a number, all right? That's your pH. All right, so the next one, we asked ourselves the same question. Is it an acid, a base? Is it strong or weak? KOH, what is it? It's a base. Is it strong or weak? Strong. Here's the hint if it's a weak base. I would give you a K value. If it's weak, I give you a K, because weak things have chemical equilibrium. Strong things have a K value of infinity, so I don't give you one. So here, this is a strong base. So we're going to make the assumption that this is the same concentration of hydroxide. So when we take the negative log of this number, what am I calculating? POH, yeah, because this is OH minus concentration. So you'll get a number. Okay, I'll just actually write a number, I guess. Negative log. There is no key. It's all in my brain. The first one, the pH is 1.92. So this next one, the POH is also 1.92. But this is the POH. To get the pH at 25 degrees Celsius, you subtract from 14. So this is 12.08. All right, that is a basic pH. All right, so calcium hydroxide is also a strong base. So does that mean that concentration is also my hydroxide concentration? Can I say that? Nope, what's the difference here? There are 2 hydroxides. So what is the hydroxide concentration here? It's double, so 0.024. And so whatever number that is, negative log of that number, 0.024 is your POH. All right, and then your pH is negative that, or 14 minus that, all right? So the only difference here, both of these are strong bases, but calcium hydroxide gives me 2 hydroxides per 1 unit. So I double it. Okay. All right, what's the pH of HA where Ka equals that? So HA is a what? Acid or base? Acid, because there's H present. Is it a strong acid or a weak acid? It's a weak acid. How do I know? I give you a K value, yeah. So if there's a K value, it means we do an ICE table. So in a Ka expression, you want your thing to act like an acid. So Ha, acting like an acid, produces H plus and A minus. Everything is aqueous. So how we do our ice table here, this is the one that we always make an approximation, is say, okay, my initial concentration on the bottle is 0.012 molarity. This reaction must move forward. So at equilibrium, I have 0.012 molarity minus X of the original HA, but X amount of H plus, X amount of A minus. So if I plug this into the Ka expression, which is H plus, so products, A minus, over HA, and everything's a nice 1-to-1 ratio, so nice and easy. Let's plug in those equilibrium values, variables. So we get that Ka equals X squared over 0.012 minus X equals Ka. I give you, it's 1 times 10 to the negative 4. So this requires the quadratic. Do you want to do the quadratic on the exam? No. So what are we going to do? Approximate and just say minus X can be real small. Let's just ignore it. So 1e negative 4 times 0.012 square root of that. And we get that X is equal to 0.0011. And we do see, yeah, it is rather small, right? And so when we do that, the X is equal to the concentration of what? H plus. And I know that because of the ice table or because you used Ka. A stands for acid, so X is equal to H plus concentration. If we did this for a base, we would do X squared over concentration equals Kb, but X is equal to hydroxide concentration. So simply negative log that and you get the pH is 2.96, right? Molarity. All right, so that's our strong acids, weak acids. All right, let's keep talking about equilibrium and solubility. So solubility has to do with dissolving solids in water. So here I give you a solid, just a generic solid, MOH3 of them, and there is its KSP. Ka stands for acid. KB, B stands for base. KSP, SP stands for solubility product. So it's good to memorize that solubility product means you throw the salt into water, it dissolves into its ions. So what's good to do is just start with the KSP chemical expression. Throw this into water. What do you get? You get metal 3 plus, you get a metal ion, but then you also get what? 3 hydroxides. That is the KSP expression. Both of those ions are aqueous, right? That's the KSP expression. So this has a value. What would be useful is to get this in terms of molar solubility. Molar solubility comes from the ice table where X is molar solubility. So where that comes from is throw in a chunk of solid. Initially, when you throw in that chunk of solid, the reaction must go in the forward direction. So in the change line, you have minus X, plus X, but then what's last? Plus 3X, yes. So at equilibrium, you have an N minus X of the metal hydroxide, of the solid, sorry, X amount of the metal, 3X of hydroxide, right? What molar solubility is the minus X. It's how much solid you lose. That is molar solubility right here. But we see that X show up in a lot of places, so it's best of us to use the KSP expression to solve for this. So solubility is that X. What it represents is how much solid you lose. But what we're going to do is actually use the concentrations of stuff to help us. The question told me that the value of KSP is 1 times 10 to the negative 8. But we can write via this KSP expression that KSP equals the metal concentration times hydroxide concentration cubed. But now let's put those equilibrium concentrations in that are in reference to molar solubility, and we get that X replaces the M3 plus concentration, but 3x replaces the hydroxide concentration, but there's a cube. So this is all equal to 1 times 10 to the negative 8. And so if we simplify all of those x terms, 3 cubed is what? It is not 9. It's 27, yes. Just, you have a calculator, so make sure you use it. It's not 9. That's 3 times 3. 3 cubed is 27. So this is 27x to the 4th equals 1 times 10 to the negative 8. And I think if you solve for this, you solve for x, you get 0.0044 molarity, right? So that molarity, what it means is that if you make a saturated solution of this metal hydroxide solution, you should measure a concentration of 0.0044 molarity MOH3, right? That's the concentration of that solid present, right? But here's the thing. Molarity, like, I don't really understand how much that is. Like, is that a lot? Is that a little? I don't know. So what might be more useful is to represent these concentrations in mass solubility. So we just got molar solubility in molarity, all right? We just got 0.0044 molarity metal hydroxide. If I were to rewrite this as a fraction, what this means is 0.0044 moles of that solid is dissolved in every 1 liter. Do you know, like, how much 0.0044 moles is? Like, is that a palmful? Is that a tiny bit? I don't know. I don't know how much that is. So if I give you the molar mass, let's convert that to a mass amount. I can wrap my head around masses. So let's look at this information given. I tell you that this solid weighs 100 grams per mole. So that means 100 grams equals 1 mole. So where does 100 go in my next fraction, on the top or bottom? On the top, because right now I'm in the unit of moles, so I put 1 mole on the bottom. 1 mole of that equals 100 grams, so I think I can do that math. 0.44 grams of this salt can dissolve in 1 liter. I understand that. Half a gram, that I can like wrap my head around how much that is to dissolve in a whole liter's worth of stuff, right? Okay, so I think we have enough time to just do these two and then we're good. Okay, all right, so if here's a chemical equilibrium, I should write that it's an equilibrium or whatever, okay? A goes to B, so 2 B's, and I tell you here is the delta G of this reaction. So if this is a chemical equilibrium, earlier in the chapter I asked you, predict does the reaction go left or right? Does it go forward or reverse? Well, all that time you were actually predicting the sign of delta G. Delta G, when a reaction is spontaneous in the forward direction, is negative. When the reverse reaction is spontaneous, delta G is positive. So we can relate all these things to K as well. So if I tell you that delta G is this value, all right, let's solve for K. So here, if I give you delta G naught, R is a constant, temperature is at standard conditions. We're just simply plugging and chugging, solving for K. K, the equilibrium constant for this reaction, is related to its Gibbs free energy as well. So it's just plug and chug, make sure Gibbs free energy is in the right unit. So 40.4 times 10 to the 3 joules equals negative 8.314. Joule mole Kelvin, that's why it's in joules, 298 Kelvin, ln K. But even before I calculate K, is K going to be a big number or a small number? Small, yeah, because delta G is not very spontaneous, so a lot of reactants are going to be present. I think if you calculate this, I think it's 8 times 10 to the negative 8. It's about that. All right. So it's really small, yeah. It's about. All right. Okay. I need to sneeze. Excuse me. All right. So, K, that is, if we let this reaction go to equilibrium, that is the ratio of products over reactants. So let's say we set up the container so everything is 0.1 molarity. What is delta G? Do you think we're at equilibrium at these conditions? Probably not. Because why else would I write this equation with Q? So it sounds like I have to calculate Q and relate it to delta G to predict which way the reaction has to go. So these are the given concentrations. So why don't we plug those into Q? Right, and I have Q right here for you. Q is B concentration squared, so 0.1 squared over A concentration 0.1. So this is equal to 0.1. That's Q. Let's relate this to K. We just got that K is 1 times 10 to the negative 8 or something. So which one's bigger? Q. So what does that mean? I have too much reactants or products? Products. So which way does my reaction have to go? Reverse, backwards. So what does the sign of delta G have to be? Positive. Do you want to prove it using numbers that it's positive? Yes. And we do that by plugging the Q into this new delta G equation at non-standard conditions. So we solve for this. So we're using this equation. We're solving for delta G. I gave you delta G not earlier in the question. R and T are given or constants, and we just calculated Q. So it's just plug and chug here. So delta G without at these non-standard conditions, when everything is 0.1 molarity, is equal to 40.4 times 10 to the 3 joules, that was already given, plus 8.314 times 298 times natural log of Q, so 0.1. If you plug all of that in, you should get a positive number, meaning the reverse reaction. The reverse reaction is spontaneous, and that's exactly when we compare Q and K also does. So, you know, the quick and dirty way we did Le Chatelier is actually explainable by thermodynamics. All right, so that's the end of it. So thank you for joining me on this journey and entrusting me, following me into the dark. So, yeah, no. We'll review, we'll still have that review session on Tuesday. I'll post updates on our Carmen site. Have a good one, everyone. I still have office hours if you want to hang out. Or ask about Honda Ridgelines. Where's my block of wood? It's right there. If you want to sign it, you can come up here.